Thank you. So yes, I'm going to talk about neutron stars, maybe a bit continuing what Ashika was talking about. And here we are also concentrating on like the microscopic structure of space-time, and I'm going to talk about this article, but yes. So what do I mean by that? Well, we basically mean extra dimensions. So we are trying to see if, in a simple way, if extra dimensions exist. They could be a solution to many questions of modern physics, and of course there are multiple complicated theories with extra dimensions, but we use a very simple one. I will talk about that in detail. And the other thing is that we want to look at it in neutron stars because neutron stars is such an extreme environment that if there are extra dimensions, then we can expect some effect in neutron stars to appear because of extra dimensions. And we want to do neutron star oscillations, basically. That's the future plan, actually. So modeling neutron stars, Ashika has already talked about this, so I don't have to say so many things now, but basically we need two ingredients. And one of them is that we need a theory of gravity. For us, this is going to be the extra dimensional theory, Kaluza-Klein theory. And the other thing is that we need an equation of state, which describes how pressure and energy density relate. And so basically, that's also a big question because we don't know how the neutron star equation of state looks like. Many people are looking for that. And then we can model neutron stars and calculate with these two equations, basically, or two ingredients, and compare it to observables. And what are the observables? Are the most obvious observables are neutron star masses and radius. But there are also other things, tidal deformability, and then there are dynamical things, star quakes, neutron star glitches, different oscillations, and of course, gravitational waves. And the thing is that comparing to observations is really difficult in a sense that it doesn't give us too much information on how the equation of state look like. Because also the measurements are not that precise. These objects are very small, very compact, so it's difficult to measure them very precisely. And also, for example, there are not too many gravitational wave detections on neutron star mergers. So how can we? Well, okay, first I will talk about the extra dimensional theory. So we basically have the usual time direction as always, and then 3 infinite spatial dimensions, and then one more extra dimension, which is a small compactified circle, basically. So the idea is that you don't see this unless you go to very high energies or somehow probe very small distances. And this is the 5-dimensional Kaluza-Klein space-time, basically. Yes. And so what are our possibilities? Well, we were actually looking at 2 different ones. The first is that we allow particles to move in these extra dimensions, and in that case, there will be no modification to the space-time. Actually, I mean, we look at it from a 4-dimensional effective point of view, but because the particles are moving in this extra dimension, they will gain some momentum in the extra dimension, in this K5. And this depends on the size of the extra dimension and the excitation. So basically, this will have different levels of excitation. And this creates a sort of a hadronic spectrum, and then we put these kind of particles with some effective mass, depending on the size of the extra dimension, into an equation of state. And then we will have a modified equation of state. The other thing that we did, and which I'm going to talk a little bit more about, is that the extra dimension actually appears as a scalar field. Nothing is moving in the extra dimension, but it's basically becoming a scalar tensor theory of gravity. And in this case, the spacetime is going to be modified. And that's also not all, because we take into account one more effect. This is actually not connected to the Kaluza-Klein theory, but basically, usually when we simulate neutron stars, we think about some background spacetime, and then some equation of state, but the equation of state doesn't take into account effects from gravity. So, but we don't really talk about classical particles, but we think about quantum particles. So the assumption is that there will be some the gravity should be taken into account in the quantum description of particles, basically, and we will get a modified Heisenberg uncertainty relation. And the most general form of doing that is the generalized uncertainty principle. This is very common in modified theories of gravity. And this basically assumes that at very high energies, there will be some finite length that we will reach. You cannot probe infinitely small structures, or there will be a maximal momentum. These are basically equivalent. But we don't go to that high energy, so this would appear at like Planck length or something like that, Planck energies. But we see that already in neutron stars, there could be some similar effects, but because of gravity. So basically, we will have a modified Heisenberg uncertainty principle, which will have a modification which depends on space-time curvature. So this is our main focus. And this is the same equation, it's just with some more complicated mathematical description, but this is basically says that there's a modification based on the curvature. And our spacetime is going to be modified. So here, this is the Schwarzschild spacetime of a static spherically symmetric black hole. And then in the Kaluza-Klein theory with one extra spatial dimension, which is taken into account as a scalar field, we will have some modifications in the powers, and this AB and D are constants, and D is proportional to the scalar field or the size of the extra dimension. And basically, if this D is 0, then there's a constraint, and A and B are going to be equal. And in that case, we just get back the Schwarzschild solution. So we basically here have one more parameter to describe some Schwarzschild-like solution. And what you can see here is this curvature as a function of the size of the extra dimension or the scalar field. It's a ratio in the Kaluza-Klein and the general relativistic case for different distances from a central object or a black hole. And basically, if D is 0, then it is exactly the same as the general relativistic solution. So they are the same, but of course, there's also a modification in general relativity. So this doesn't depend on the theory of gravity, really. It's just a space-time curvature. And but in the two theories, it's different. So the question is if we can measure this difference somehow. One way would be to look at the dispersion relation, which also gets modified. So basically, if we can rewrite the uncertainty relation into a modified dispersion relation, then we are also going to get an effective mass of the particles. And the thing is that this effective mass correction is very, very small. But if we go close to the horizon of a black hole, then it diverges. And in that case, this can result in negative effective mass squared, which is basically says an imaginary mass. So you can think of it as particle decay or maybe even Hawking radiation. So that could be one way of thinking about it or interpreting it physically. But of course, this is quite difficult, or it would be very difficult to measure something related to this. So instead, another approach would be to look at the equation of state again, because although we don't modify the equation of state directly, gravity would also play a role in it. So this modification to the Heisenberg relation could lead to a modified equation of state, also modified thermodynamics, and then we can come back to modeling neutron stars again. And then maybe there would be some observable effects. So we didn't come to simulating this yet, but that's basically the goal. And the thing is that now I will talk about a little bit of how we do this in general and how we did it in the case where we had particles moving in the extra dimension. And this was for an isolated neutron star, static, spherically symmetric. And we basically get the mass radius curves. And the most important here, observable here, was the maximal mass. So we have these mass radius curves. We have 3 parameters. One is the size of the extra dimension. The other is how many excitations we allow, and there's a repulsive force between particles. And then we simulate all these curves. And basically, you have to simulate a lot of curves like this. Each of these curves has like 30, 50 stars. Now I don't remember exactly. Each point is a star. And then if you want to do like a more statistical analysis or to see something, then you have to do a parameter space scan. And here on the right-hand side of the figure, we plotted only the maximal mass of the stars. That is more critical in constraining the equation of state as a function of the size of the extra dimension. And then here, each point comes from one of these curves. So we already have like 10,000 or something like stars simulated. But so far, because everything is static, it's still quite cheap numerically. But the thing is that many equations of state satisfy this kind of observational data, basically. And a lot of times people don't even put in an exact model of nuclear physics, but just something which satisfies a few assumptions like causality and thermodynamic stability, and then we say something statistically. So what can we do? And the next step would be to look at something dynamical. Mergers or oscillations of neutron stars. Of course, the most famous ones are the gravitational wave observations, and this is actually the first observation. So this is for black holes, but basically what people mostly study nowadays is the F-mode oscillations, because these appear in the ring down part of this sinus. So after the merger, basically, there's a remnant of neutron stars, and those are still oscillating, and they have a peak, which could give some more information on the equation of state. This is a quadruple oscillation, this F mode. So this produces gravitational waves, and this is in the kilohertz regime, which means that LIGO Virgo can already observe it, but it's not very sensitive to that. But future detectors, such as Einstein telescope or Cosmic Explorer, should be much more sensitive to these. And then possibly with those observations, we can constrain the equation of state much further. But of course, to simulate neutron star mergers and these kind of oscillations, we need to do dynamical simulations. Those are much more expensive numerically. You don't necessarily have to do full general relativistic treatment, but it gives a much better result. So that means you have to solve basically back reactions from the gravitational field also. So this becomes immediately much more difficult. And that is basically how you can say, or possibly you will be able to say more on the equation of state of neutron stars. That would be a next step in this neutron star-based studies. And so I'm coming to my summary. So we basically look at extra dimensional theories. The Kaluza-Klein theory as a simple sort of effective model of extra dimensional theories, where we have one spatial extra dimension, which is a little compactified one. And the other thing is that we also took into account if there are some modifications to the equation of state inside neutron stars because of gravity. And if this could give an effect, and if it gives a measurable effect, then does it say anything about can we differentiate between different theories of gravity based on this? And then we also put modifications to the equation of state itself based on the theory of gravity, or just this just simply gravity or different theories of gravity. And basically, for now, we just did static modeling of neutron stars, which is already computationally can be quite heavy if we want to do a good statistics. But the future goal is to go to dynamical simulations, which is even more complex. Thank you.
Thank you for the nice talk. Is there any question for Anna?
It was a very nice talk, Anna. I have one question for you regarding the oscillation. So since you modified the space-time with adding this kind of compactified small dimension, the Einstein's equation will change consequently. So if you are using a perturbative theory to decompose the perturbations into polar and axial modes, in which the polar mode will produce the F mode oscillations, they will also carry contributions from the modifications. So they won't be the same like in normal GR. I don't think that in this special setup it has been derived yet. So first you try to apply purely GR oscillation models pulsation, or already adding these additional contributions?
So basically, we are in the very beginning of the study. So we haven't. The first, we just want to do normal GR, and in the simple model where we allow particles to move in the extra dimensions, and in that case, there will be no modification to the space-time, only through the equation of state, basically. And then the next step would be to look at the case where the space-time is also modified.
Thank you very much.
Thank you.